Good morning, everyone. So, today I'm going to go over homework 10.3. I suggest you try it yourself first, then check the written copy of the answer key that's posted on both Classroom and Drive, and then watch this video for the parts that you're stuck on. So first off, number one. For number one, go into the PhET simulation and sketch the path of the rays as they pass from air into water. Now, refraction is not obvious when light travels from air into water and hits the surface perpendicularly. And remember, this is because when we hit the surface perpendicularly, as shown, the wave fronts both hit the water-air boundary at the same time. So if you imagine these lines that I've drawn here, imagine these are the crests of the wave. Remember transverse waves, so these are crests, crest, 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 crest. Both of the crests, both sides of this green crest, are going to hit the air-water boundary at the same time. So when the light travels from air into water, the wavelength will get shorter. So crest, 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 really close together. Slow means small wavelength. But since they both hit at the same time, they don't have any refractive bending. So just to reiterate, this is slow medium, long wavelength. This is, oh, I said that wrong. This is fast medium, long wavelength. There we go. Slow medium, small wavelength. Long, fast. Okay, so now let's keep going. As you draw these, an important thing to keep in mind is that angles, and we'll talk about this more on Thursday, are always going to be measured from what's called the normal line. And the normal line is a line that where your ray hits a boundary forms a right angle. So I'm going to draw some normal lines for the remaining three examples. There's my dotted normal line. It's perpendicular to the boundary where the ray meets the boundary. Perpendicular to the boundary where the ray hits the boundary. And in the faster material, that's the air, it should go with a larger angle. So here's my initial angle, my incident ray angle. It should have a fat angle and a fast material. Then that material goes from air into, or that ray goes from air into water, and it bends towards the normal line. It goes from fast to slow, so the refracted ray is a smaller angle. Slow material, slim or smaller angle. Now, that being said, this was all taken from the PhET simulation with the normal line drawn in. And if you wanted to do this with the other two examples, you could just put in angles. You could make this, I don't know, 15 degrees, 45 degrees, 60 degrees. Put it into the PhET simulation, and then get the incident or the refracted angles as they come out. This would be some number less than 45 degrees. I'm going to guess this is probably right around 30. Draw a 30-degree angle. You'll notice it's a little bit less steep, not parallel to the one next to it. This angle should be smaller than the original. And this one should be even slimmer than that, so even steeper. In number one, you're asked to draw 4 rays as they pass from air into water. So what I'm going to have you do is open up the PhET bending light simulation, and I want you to change the second material to water. For ray 1, the wave hits perpendicularly to this air-water interface. It goes exactly along the normal line, and if we measured it, its incident angle and refracted angle would both be 0. For the second ray, it's at about 15 degrees or so. So let's say I move this out here. Making 15 degrees the incident angle, some small angle in, makes it about 10 degrees as the refracted angle. Now I'm just estimating this off the top of my head from what I'm seeing in number 1. So as long as you pick for the next angle some larger angle, I went with 45 in my answer key, which is about here-ish, then I'd see it still bends towards the normal line. So a fatter angle, in this case 45 degrees, in the faster material, a slimmer angle, like 31 degrees, in the slower material. And reminder, based on yesterday's lesson, that's because as the wave hits this barrier, it changes direction and changes wavelength. Okay? Next ray out should be some angle above your third angle, so let's make it really big. Let's say we make it like, 80 degrees. 80 degrees is my incident angle, and something like, what is that, like 47 degrees as my exiting angle. And that's all you had to do for number 1. Now, if you didn't put in individual numbers and try to sketch it out and use the protractor, that is okay for now. And in fact, on Thursday, I'm going to give you a way to not only measure these angles, but predict them mathematically. So, speaking of math, so far in this unit, we've used 3 equations. We've used this regular speed equation. This is good for anything traveling at constant velocity. We've used the wave equation, true for any wave. And in the video, you watched this introduction where V is C over N. So I wanted to break down what that meant just in case you were confused on lettering here. This value N is the index of refraction. N for index. And the index of refraction is some number between 1 and about 2.5 that's related to the material you're dealing with. It's a ratio, and because it's a ratio, there are no units. So air is easy for light to get through, so it has a low index of refraction. Water is a little bit harder for light to get through. It slows the light down, so its index is 1.33. Diamonds are apparently this shiny because they actually have a super high index of refraction. This is about the maximum you can get. After about 2.5, that means that an object is so optically dense, it is most likely going to start to be opaque. In this equation, we have the index of refraction, which has to do with the material that light is traveling through, or the medium. C is just 3 times 10 to the 8th. And V is how fast the light travels in medium. So that V is still speed, but it is speed of light in material, in the medium. So now let's practice using it. I'm calculating the speed of light in glass. I have the wavelength, but not the frequency, so I can't use that. I don't know anything about distance or time, so I can't use that. It kind of makes sense that I'm trying to use this equation I just introduced. So, speed of light in material, I'm using this third equation here. That's C over N, that's 3 times 10 to the 8th, over glass 1.5 for the index, giving me 2 times 10 to the 8th meters per second. And let's just double check here. When light goes into a denser medium, it should slow down. It should make a smaller wavelength. Slow speed, small wavelength. You can kind of imagine this as, for instance, like pebbles being thrown off the back of a boat at a constant frequency. If the boat's going really fast, those pebbles will be far apart. If the boat slows down, those pebbles will be all close together. So, in this case, I expect that red light wavelength to decrease. In fact, I later say calculate the wavelength, so I know the wavelength's going to change. I obviously know the speed is going to change because we just calculated that. The thing that doesn't change is the frequency. And how do I know that? Is because the frequency of light gives us its color. Hey, when red light goes from air into glass, is it still red, guys? Like when I go swimming in a pool, all the colors still look the same. My swimsuit doesn't suddenly change from like yellow to orange. Neither of those would be great swimsuit colors on me. But in any case, the frequency stays the same, and I know that the frequency stays the same because I still observe that color as red. I know wavelength changes because as it gets to a slower material, then that slower material makes the wavelength smaller. And I know the speed changes because we literally just did that. So calculate the wavelength then. I have the new speed, I have the old wavelength, and Mr. Lubin introduced this equation. The new wavelength is the old wavelength divided by the index. So I'm going to put O for original. If the original wavelength was 650 nanometers, you could do that divided by 1.5. And that would get you your 433. But since I didn't include that in that equation sheet, there is a second way to do it. Or, alternate method, use our wave equation in air to find the frequency. And know that the frequency in air is the same as the frequency when it goes into the material. In air, light travels at 3 times 10 to the 8th meters per second. 650 nanometers is 650 times 10 to the negative 9th meters. So the frequency in air would be 3 times 10 to the 8th divided by 650 times 10 to the negative 9. And I would expect really high frequencies. When we were dealing with sound, the frequencies were in like the hundreds. Notice that the frequency for light is in like the billions and billions. The reason that we would use this wavelength equation instead of doing this method is this is actually 2 steps. Now that I know that it's going from air to glass, I repeat this, but I change the speed in order to find the wavelength. In air, I find the frequency. Now I repeat this in glass, substituting in the new speed. In air, the speed was 3 times 10 to the 8th. In glass, the speed was 2 times 10 to the 8th. The frequency stayed the same, so that's 4.61 times 10 to the 14th. Divide by that on both sides. And that gives us 4.34 times 10 to the negative 7th meters, which, by the way, is equal to 433 nanometers. Someone asked me in an email, so thing to point out that you might need to know, which units are you going to need to be able to convert between? Nanometers is going to be a very common one. And in this unit, we're going to deal with nanometers. Hundreds of nanometers will be approximately wavelengths of light. For part 3, open up the PhET simulation bending light again. Make sure you change the media to mystery B. So it should look something like this at this point. You're going from air to an unknown material B. And as your red light travels from air to B, it bends. In air, its path would have been here, but it bends towards the normal line, making a smaller angle. In this case, let me draw on the normal line in another color. In orange, remember the normal line is the perpendicular line to this surface where the incident ray meets the boundary. Okay, how to measure the speed of light in the medium is to grab that indicator, the speed measurement tool, and if you read off from there, it says 0.71 C. This indicates that the speed of light in the mystery material is just a fraction of the speed of light. Substituting in 0.71 times 3 times 10 to the 8th gives me a value of 2.13 times 10 to the 1/8 meters per second. So if you are reading from the old version of this, it has this typo here. If you read this document after 10:50 a.m. this morning, you have the new document with the correct number. Sorry about that. So we know its speed is 2.13 times 10 to the 8th. Let's find n. The only equation so far in this unit that has an n in it and relates speeds looks something like this. So I'm saying 2.13 times 10 to the 8th is equal to 3 times 10 to the 8th over n. Cross multiplying, this means that n is equal to 3 times 10 to the 8th over 2.13 times 10 to the 8th. The times 10 to the 8th cancels, and 3 over 2.13 is the 1.41. Now, to double check, I know I mentioned this earlier, but the index of refraction is some number between 1 and 2.5. If you accidentally divided in the wrong order and got some number less than 1, like 0.7, well, that's actually not possible. So that's an indication that you divided incorrectly. So now let's say we've got this light, and we use waves in order to send signals. And it might sound silly, like why would we use light to send signals? But that's what fiber optics cables are for. The optics in that root word there has to do with sending information using light. So this is kind of a silly one. Let's say I'm going to use light and I'm going to send it directly across the ocean. In this case, this is water as the medium. So what I would do to calculate the speed of light in water is take our index of refraction equation, substitute in 3 times 10 to the 8th, and then pick out from the front page n for water is 1.3. That gives me my 2.25 times 10 to the 8th meters per second. So it's not going to take very long at all to cross the ocean. I would use the relationship between time and speed and distance in order to solve for time. So that's 2.25 times 10 to the 8th is equal to 3 million, so that's 3 with 6 zeros at the end, over t. Cross multiplying, that means t is equal to 3 million over 2.25 times 10 to the 8th. And if you plug in this calculator and you get a really big number, chances are you forgot to put parentheses around this bottom term. Putting parentheses around this bottom term gives you that small time as expected. It's one of the reasons we use light to send signals, because even though it's all the way across the Atlantic Ocean, it still takes, an extremely fast time to get there. Last problem, and if yours looks different from mine, that is okay. I'm using the unedited copy, so if you're looking at this after 10:50, then yours looks better than this. Sorry about that. So let's do the normal lines. There's 3 more of them. Normal line is a perpendicular line that we use to measure. And we'll use that to measure wherever the incident ray hits the surface boundary. So there's my 3 normal lines. Check. Now we're going to use this fast, slow, slim, fat relationship here that on Thursday we will learn an equation to help us picture this. So what I'm going to do is I'm going to look at my incident and refracted angles. The fastest material will have the fattest angle. And you can pull a protractor out here if you want. I know there is an angle measurement tool on your iPads for this. But if I'm ranking them, C is the fattest angle and therefore the fastest material. A has a large angle, but not quite as big as C. C is almost 90 degrees there. I don't know if you can see that. And then B is the slim angle. Slow material. So in this case, C has the fastest speed, then A, then B. Okay, let's do it again. So B is the fattest angle. And double check your angle. It's always the angle between your ray and the normal line. So if you're looking, it should have one dot on the normal line, that perpendicular. It's why in part A I had you do that first. And the other dot is your ray. So B's angle is largest. This must be the fastest material to have the fattest angle. Then C, then A. Okay, now index of refraction. This equation, that V is equal to C over N, means that N is inversely related to V. And just to be clear, let's double check this. That means it goes fastest through air because small index, fast speed. And slowest through a diamond, large index, slow speed. A diamond has more particles in the way, so the speed is slow. Air has no or very few particles in the way, so the speed is fast. And that inverse relationship means that whatever my ranking was for the first part is just opposite. So B, A, C, B. Okay. For this ranking problem, I remember that wavelength and speed are directly related. Remember that when we're talking about materials here, fast material has long wavelengths, slow materials have short wavelengths. So that means, since they're directly related, whatever I ranked earlier, my CAB here, stays the same. CAB, that these two should match each other, and these two should match each other. However, for 5D, they should all be the same. So this is one of the reasons I edited this document. Should be A equals B equals C, A equals B equals C. They all have the same frequency because they all have the same color light. Imagine violet light going from air into oil or into glass. No matter what, it's still going to be violet light, no matter what material you put it in. So the frequency stays the same.